So we left off last class, oh, I didn't start the iClicker, with talking about work and pressure systems for gases. And we were in the middle of working a problem, and I didn't want to rush it, so we did not quite finish it. And we are going to finish that. So we can relate work to negative P delta V, assuming that our external pressure is kept constant. And we started working on this problem where we had a process of a gas, and we knew how much heat was being released. Well, we knew our total energy being released, we knew our heat being released, and we knew that the external pressure was kept constant. We have 1 atm, and the initial volume of the gas is 10 liters, and we want to know the final volume. So we figured out our work of our system because we know our delta E of our system was given and our Q of our system was given. So we found our work to be negative 2,260 joules. And now that we know our work, we can use the fact that we know our pressure and we know our work to figure out our change in volume. But we can't really do that with this in joules, because if we use our W equals negative P delta V, V is going to be in liters, P is going to be in ATM, and this is going to give us ATM liters. So we have to convert that joules of work to ATM liters. So that's going to be our next step. So all I'm doing is rewriting the joules that we found for our work. And we're going to convert this to ATM liters. And again, this is something that we know. This is a given, that 101.3 joules is equal to 1 ATM times liter. So now we have this in units that we can use to calculate our change in volume. And remember, this is negative, so this means that our work is, we are doing the work onto the surroundings, so we don't want to lose that sign. That's really key when you're doing these problems, that you pay attention to your sign of whatever unit of energy that you are talking about. So we know that our work is going to be equal to negative P delta V, and we're looking for delta V. So we can solve for delta V is equal to our work over negative P. So we just calculated our work. It's in ATM times liters. And we're given our pressure of 1 ATM. So this gives us our change in volume, and this is going to be a positive number. So now that we have our change in volume, remember, our change in volume is equal to V final minus V initial. We know our V initial, we know our change in V, so now we could figure out our V final. So our V final is 32 liters. And of course that's rounded to represent that we should only have two significant figures. And this makes sense because delta E is negative, so W must be negative, so our volume should be greater. Again, we know that we can have a change in, or an exchange of heat from our system and our surroundings. And we've talked about this before. So our exchange of heat energy, our Q, is equal to our mass times our specific heat times our change in temperature. And of course, the difference between our heat of our system and our surroundings is going to be equal and opposite. And we've been talking about this. Also, our exchange in work is going to be equal and opposite between our system and our surroundings, and we know work is equal to negative P delta V. So since our delta E is equal to our heat plus our work, we can determine delta E by measuring heat and work, and that makes sense. But in practice, that's not always easy to do, especially if we're talking about a chemical reaction. It's not so easy to figure out the heat and the work of the actual reaction. So in actual practice, it's a bit easier to do a process in a way that there's no change in volume, so our work is equal to 0. And if we do that, then we can say that our delta E system is equal to our Q system at constant volume. And we can do things in the lab to make it to where the volume doesn't change in our reaction. So in practice, also, it's really hard to observe the temperature change of our system if our system is a chemical reaction. However, we can measure the changes in the surroundings because it's really hard to measure the changes in the individual chemical compounds. So instead, what we can do is take an insulated, controlled system and surroundings and measure the temperature change in it. So what we'll typically use is what's called a bomb calorimeter. And in a bomb calorimeter, it's sealed. It's an insulated container filled with water. We have a tight fitting sealed lid, and that makes the whole system stay at a constant value. So we can't lose any water or anything like that if we're doing, let's say, a solutions reaction. It's not a bomb calorimeter because, of course, it's a sealed container. So if you have a sealed system, your pressure can increase. That is something to take into account. But our volume isn't going to change, so our work is going to be 0. And that way we can figure out our delta E of our system. So if we're using a bomb calorimeter and our change in volume is 0 and work doesn't matter, our Q of our surroundings is going to equal to our Q calorimeter. So if we take the temperature inside that bomb calorimeter and we're following the change from before and after the reaction, that's going to be our surroundings. Because our system is going to be our actual reaction between our chemical compounds. So our Q calorimeter is our surroundings. So the heat of calorimeter is going to be equal to the negative heat of our system, meaning our chemical reaction, that it's really hard to measure. And because we're keeping our work at 0 by keeping our change in volume constant at 0, no change in volume, then our delta E of our reaction is going to equal to our Q of our system. So that means our reaction delta E is going to be negative if we're calculating our Q calorimeter. So our Q calorimeter is going to depend upon a constant, just like our constants before. So our C calorimeter times delta T is going to tell us our Q. So we can't just look at the change in temperature, we will still have a constant. Now, C cal can be predicted or given to you, but typically it is determined in the lab by doing a controlled system. So when you are taking your lab in this class, either you're in 113 now and you're already doing this, or when you take 110 next semester, you're actually going to first calculate Q calorimeter, and then you're going to actually use that for your chemical reaction. So this is kind of what it would look like. This is a very this is a bit specific of a calorimeter. You might have paid a little bit more of that, but we'll simulate that in lab with what we call coffee cup calorimetry. But you'll have a thermometer. Oftentimes what we'll look at in this case, we have this water. So here we have water. Here's we have our sample if we're measuring, let's say, combustion. So combustion will occur, the reaction will occur, and that will transfer heat from the reaction from our system into our surroundings, which is water. And then we can measure our change in temperature of the water. And then our Q calorimeter in this case will likely be equal to our specific heat of water, since that's what we're looking at. But if we are doing a reaction in solution, so one of our exchange reactions that we've talked about before, like precipitation, then having those dissolved compounds in the water can affect your C calorimeter. So then that would be something you'd have to calculate. So our system is our calorimeter. It's the water. Our surroundings. And our system is the reaction. And we're still going to have that change in temperature. So even though you're seeing Q calorimeter, always think that's your surroundings. So just equilibrate that in your head. So let's look at an example. So let's pretend like we have that. And we have here, our sample is going to be sugar in this example. Okay, there it is. So we have a certain amount of sugar, and of course we will need to know, well, in this case, we'll be talking about what the mass can be used for. So 1.010 grams of sugar. We're burning it in a bomb calorimeter. The temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. Now here we're giving our C-cal, and we want to know our change in energy for burning 1 mole. Now first off, we likely do not have 1 mole of sugar. So for this case, we need to know what 1 mole of sugar would be, and we could calculate that if we have the molar mass. And if I don't give you what sugar looks like or the molecular weight, the formula of sugar, then I would give you the molar mass. It's not something I expect you to memorize. I always give you that information. So what are we looking at here? So first off, what are our givens? We have our mass. Of our sugar. This is what's burning. And we have our T initial, because it told us it's rising from 24.92 degrees C in the bomb calorimeter. So this is our T initial of our calorimeter. And then we have our T final of our calorimeter, which is 28.33 degrees C. Now there's one thing to note, and you should note this right away. The temperature of the water, which is our surroundings, is increasing. So that means our system is giving off heat. So you should already know that your Q of your calorimeter is going to be increasing, so your Q of your system will be negative. So you should recognize this right away once you figure out your T final and your T initial. And if you think about it this way, then these calculations make sense. And you're not so much just plugging in for calculations, but actually using what you understand. So we have our C-cal that's given to us. In kilojoules over degrees C. And what we're looking for is our delta E per mole of sugar. So of our system. So our conceptual plan, where'd it go? We have our Q-cal is equal to C-cal times our change in T. So we have our C-cal, we have our T initial and T final of our calorimeter, so we can figure out the heat that is being transferred into our calorimeter. Once we figure that, we have our Q reaction. So our delta E is going to be equal to our Q reaction, but we want our delta E per mole. This is specifically asking for our change in energy per mole. So we're going to take our delta E and we're going to divide it by the amount of moles that we have. So we have it per mole. That's the only difference, and this specific one is asking per mole. So we'll calculate our Q calorimeter, and then we'll know our Q reaction, because these are going to be equal and opposite, and we already know the sign that this is going to be based on our initial temperature and final temperature. Then we can figure out our delta E per mole by just dividing our delta E by the amount of moles that we have, and if we have our molar mass, we can calculate that very easily. So let's look at that system. So our change in temperature of our calorimeter is going to be equal to our T final minus our T initial that we have here. So that gives us a delta T of 3.41 degrees Celsius. And of course it's positive. And that makes sense because our temperature is increasing of our calorimeter. Now to figure out our Q of our calorimeter, we take our C calorimeter and multiply it by that delta T that we just calculated. So this was given to us. Our degrees C cancel out, and notice this is going to give us kilojoules of energy because of what our C cal is in, which is kilojoules per degree Celsius. So watch your units of that constant. So that gives us a Q of positive 16.709 kilojoules, and that makes sense because our temperature is increasing. Now to figure out our Q of our reaction, our Q cal is just going to be equal and opposite of our Q reaction. If our Q calorimeter absorbed heat, our Q reaction had to give it off. So our Q of our reaction is negative 16.709 kilojoules. Now we are using our bomb calorimeter, so our delta V is going to be 0, so our work is 0. So therefore, our delta E of our system is going to be equal to our Q of our system, or reaction. I know I put reaction. Our reaction is our system. So that's going to be equal to negative 16.709 kilojoules. Now that's for 1.010 grams of sugar, but they want to know the delta E of the system per mole, which is going to be more useful in the long run because we could relate that no matter how many grams of sugar if we knew our delta E per mole. So we need to know how many moles of sugar we actually burned, and we can do that. We've been doing that for a while in this class. We need our molar mass of sugar. This is our and I would have to either give you the molar mass or give you the formula for sugar. I don't expect you to have that memorized. Also, the term sugar is, are we talking about table sugar? Are we talking about sweet and low? You know, it makes a difference for that formula. So I'd be more clear with that. That's something that you would be given. But we can calculate that to 342.3 grams per mole. So we want our 342.3 grams at the bottom and our 1 mole at the top. And that means that for this reaction, we actually burned 2.951 times 10 to the negative 3 moles. So to figure out our change in energy of our system per mole, we're just going to take our change in energy per system and divide it by the amount of moles that we actually used in the reaction. And our units are going to be kilojoules per mole, because kilojoules and mole don't cancel out, so those units are both there. So that makes sense. And it also makes sense, and that's going to be a negative number, bless you, because we are losing heat in the reaction, because the calorimeter is increasing in heat. So that brings us to this term that we use in thermodynamics called enthalpy. So enthalpy is H of a system. This enthalpy is the sum of the internal energy of the system and is a product of pressure and volume. And it is a state function. It's related to our energy plus PV. Now typically we don't look for H, we look for our delta H, our change in enthalpy. And we're usually relating this to a reaction. So our enthalpy change, our delta H of a reaction, is the heat evolved in a reaction at constant pressure. So our delta H of a reaction at constant pressure, because this is constant, is going to equal to our Q reaction at constant pressure. And this is why typically we consider delta H to be our heat. But this is our change. What does this mean? We want to know the difference of our internal energy of the system before the reaction versus after the reaction. And that's what we're going to look at. Usually delta H and delta E are similar in value, but it can be different, especially if we produce or use large quantities of gas, because that's going to affect the pressure a lot. So if we produce a large quantity of gas in a closed system, that's going to increase the pressure a lot. We're using a large quantity, that's going to decrease the pressure a lot. And when pressure is not constant, that's going to affect how delta E and delta H look. But for a lot of cases, our change in energy and our delta H can be very similar. So we're going to talk a bit about delta H and relate it to reactions. I actually have one more for you. So cold in here. Freezing. I'm going to start doing jumping jacks up here. So let's talk a bit about our enthalpy and some terms that we use in chemistry. So you may have heard endothermic and exothermic. And what we're discussing when we're talking about endothermic and exothermic reactions is a way to describe the change in delta H between our reactants and our products. So again, all molecules have an inherent amount of stability or instability. And when we're looking at reactions, most molecules, we can force things to happen, but they want to be in the most stable state that they possibly can be. So what we're doing is comparing really the potential energy before a reaction versus the potential energy after the reaction, and looking at the difference of those energies. So if we're starting with a reactant that's really unstable, we usually will call that reactive, and it's going to have a higher potential energy. And if the product is more stable, it's going to have a lower potential energy. And what we're going to relate is our change in energy, and mostly we're going to look at heat energy. So that's our delta H. Now later on, you're going to get more into this. This particular chapter is thermochemistry, so we're working on heat. But in some reactions, and not all, but in some reactions, our change in energy from reactants to products is affected by more than just delta H. It's also affected by what we call delta S, or our amount of disorder in the system. But we're not going to be talking about delta S in this particular chapter. You will be looking at that later in 106. And we'll really talk about it in organic chemistry if you end up taking that class. So right now we're focusing on delta H. So when delta H is negative, heat is being released from the system, and we call that an exothermic reaction. The surroundings are going to feel that heat. And let's say we have a reaction going on in a flask and we're holding it in our hands. If it's exothermic, then you're going to feel the heat generated by your hands getting warm because you are the surroundings and the heat is being transferred to you. When delta H is positive, heat is being absorbed by the system, and the reaction that, since it's absorbing heat, we call it endothermic reaction. So exothermic heat is given off, endothermic heat is going in. If you think about a cold pack, or what happens is you break that pack, and then the chemicals are released to where they can react with each other, and it's a endothermic reaction. So it's pulling heat into the system, but you feel it as cold because it's pulling heat away from the surroundings. And of course, we know a lot of exothermic reactions when we talk about combustion reactions, things like that that produce energy. So we have chemical heat packs and chemical cold packs, and basically heat packs, you break the little thing inside, it allows the reactants to mix, and then that is an exothermic reaction and it gets hot. The cold packs are opposite. A cold pack is NH4NO3. It dissolves in water in an endothermic process and pulls energy into it, and therefore it feels cold. So when we're looking at this, combustion is going to give off heat. We're looking at the melting of snow. Melting of snow is taking in heat from the surroundings, so that would be endothermic. Evaporation of ethanol is again taking in heat energy to go from one system to another. Sublimation is, remember, sublimation is going from a solid to a gas without going into the liquid state. So like CO2, dry ice. That's how CO2 is. Dry ice is just CO2 in the solid form. And it sublimates, dry ice doesn't form a liquid. It goes straight from the solid to the gas. So our ones that have a negative value is going to be combustion. It's the one that gives off heat. All the other ones is absorbing heat from the surroundings. Now, as far as which of the following is false, these are all true. Our delta H for a chemical reaction is the amount of heat absorbed or evolved, given off, in the reaction under conditions of constant pressure, because pressure can affect this. And often in chemistry, when we're studying things, we will keep certain things constant to make it easier to represent the system. The more variables you have, the harder it is to represent a system quantitatively, so we'll often do that. An endothermic reaction has a positive delta H and absorbs heat, that's true, and an exothermic reaction has a negative delta H and gives off heat. So it feels warm to the touch. So let's talk a little bit about these reactions. For an exothermic reaction, the outside temperature rises because it's releasing thermal energy into the surroundings. Where does it come from? Well, the exothermal energy comes from the conversion of some of the chemical potential energy to the reactants into kinetic energy in the form of heat. So, like I said, every compound has an inherent amount of potential energy. Is it reactive? Is it not reactive? The less reactive or more stable the compound, the less potential energy it has. So this all affects our amount of kinetic energy that can form heat. So during the course of a reaction, some bonds are broken, some bonds are formed. The products of a reaction that have less chemical potential energy than reactants, then the difference in energy is released as heat. So mapping this out, and we're going to talk about these a little bit more, but I want to introduce it now. We'll often use what's called a reaction coordinate diagram. So let's say we are doing this reaction. We know that that's exothermic. A reaction coordinate diagram is usually a diagram where you have your potential energy, so our energy, and it's always drawn from less to more, going up. And then we have our reaction. And typically, we have our reactants here, somewhere along that energy diagram, and our products somewhere here. So in this case, our reactants start off at a higher energy, and our products end up at a lower energy. And our products, this energy is the energy of both CO2 and H2O. The energy here is the energy of CH4 and O2. So it's not just CH4, it's not just O2, it's both of those energies, potential energies added together. In an exothermic reaction, our products are lower than energy in our reactants, so Q well, our delta H is negative. So when it releases, if our potential energy is lower for our reactants, for our products, then we lose that delta H, and it's left as negative energy. Now, we also will often along the diagram show some sort of path. And that path can change based on experimental conditions and different things. And we're not going to talk about that path right now because that's beyond where we are in this chapter. We're really just looking at the changes between our energies of reactants and products. Now, if we did the reverse reaction, where these are our reactants and now these are our products, our delta H would be positive. A reaction where our products are lower in energy than our reactants, we call that a spontaneous reaction. It doesn't mean it's going to happen fast. Delta H has nothing to do with how fast the reaction is going to occur. That's kinetics, and again, not what this chapter is. It only has to do with the fact that products are lower in energy than reactants, and therefore the reaction is favored by energy. So that's all spontaneous means. The formation of diamond to graphite is spontaneous, and clearly that doesn't happen very fast. When's the last time a diamond in your jewelry drawer turned to graphite? It won't, because it takes a lot of pressure to do it. But it's still spontaneous, even though it takes a long, long time to do. And it's only because graphite is more stable than diamond. That's the only reason. So when we talk about spontaneous, it has nothing to do with how fast the reaction is. So this is an example of what an exothermic reaction would look like. Of course, an endothermic reaction is exactly opposite of that. Your products are higher in potential energy than your reactants. Your temperature is dropping due to absorption of some thermal energy, and you're feeling the surroundings. Of course, a reaction, we're breaking and forming chemical bonds. Depending on the reaction, that might be covalent or ionic that we're talking about, depending on what we're doing. But either way, we're breaking and forming new bonds. So we're really looking at, and again, this is a state function. The difference in the energy of our reactants and products doesn't change, though the way we get from reactants to products might change based on our experimental conditions. So again, that is a state function. So our difference between that and our endothermic would be, for our endothermic, our reactants are going to be lower than energy than our products. And then our change in energy is going to be positive. This is what we call a non-spontaneous reaction because our products are not favored by energy. They're less stable. And again, energy is always written this way, where this is our change. In this case, we're mapping out change in delta H. So it is an extensive property. The more reactants you use, the larger the enthalpy change. So if I'm doing combustion, and again, think about this in terms of everyday life. If I'm burning wood in my fireplace, if I burn 1 log of wood versus 6 logs of wood, how's it going to affect the amount of heat coming out of your fireplace? 6 logs of wood are going to give you more heat because you have more fuel. And that's really just representing what happens in a chemical reaction. But it is related. So if I'm only burning methane gas, the amount of methane gas I can figure out if I knew how much delta E per mole is typically formed in that reaction, no matter how much methane gas I'm using. And I can actually calculate how much heat I expect to give off if I know that. So it is related to the amount. By convention, we calculate the enthalpy change per number of moles. That way it can be found any reaction we're talking about. And it is written stoichiometrically. So for this reaction, again, we're looking at combustion. We have C3H8 plus 5O2 gives us 3CO2 plus 4H2O. And our delta H for that reaction is negative 2,044 kilojoules. What does that mean? The forward reaction is giving off heat. We know that it's it is combustion. It should be giving off heat. So Even if it's a reaction you don't know, that should tell you something. This number tells me how much heat is giving off per mole of C3H8. Per 5 moles of O2, I'm forming negative 2,044 kilojoules. But for 1 mole of this, I'm forming negative 2,044 kilojoules. So again, that stoichiometry is really important. This tells me a lot of things, this reaction. I know that it takes 1 mole of this and 5 moles of this to form 3 moles of CO2 and 4 moles of H2O. But if I know my delta H of my reaction, I also know 1 mole of this forms that much kilojoules. But 5 moles of this forms that much. I know that when 3 moles of CO2 is formed, this is how much heat is released. I know that when 4 moles of H2O is formed, this is how much heat is released. So if I know my chemical reaction and I know my delta H, I know a lot. And I can do a lot of calculations. So this is a relationship, just like our other relationships of our stoichiometry and our chemical reactions gave us. If I know my delta H. And I can use this in a conversion. So let's look at an example of that. Oh. And in this case, the chemical reaction is given to you. There's nowhere anywhere good to put this thing. Okay. So let's look at an example. We want to know how much heat is evolved in the complete combustion of 13.2 kilograms of C3H8. Of course, we need to know the full reaction, and we would need to be given our delta H of that reaction. So you don't have to memorize delta H's. That's silly. You would be given them. So we just looked at this equation. I'm just going to rewrite it. So we just did this. So we know we have this much heat given, negative 2,044 kilojoules for every 1 mole of C3H8 burned. Now we are starting with 13.2 kilograms. So of course we can relate that to moles because we can figure out the molar mass. So we know we have 13.2 kilograms of C3H8. We can calculate our molar mass of C3H8, but remember our molar mass is in grams per mole, and this is given to us in kilograms. So we want to convert that to grams. Remember, kilograms are bigger than grams, so we have 1,000 grams in 1 kilogram. So we can calculate our molar mass is 44.09 grams per mole. Again, you can do that. So our 44.09 goes at the bottom, and our 1 mole goes at the top. Now at this point, we've done all of this. This is just figure out how many moles of C3H8 we have in 13.2 kilograms. And now we have the amount of moles. Now we can figure out how much heat is actually given off for that amount. So again, this is a relationship for every 1 mole of C3H8, which that 1 is dependent on the stoichiometry of our equation. We form negative 2,044 kilojoules of heat, or we form 2,044 kilojoules of heat. The negative represents as exothermic. So because we're using way more than 44.0 grams, it makes sense that we're forming a lot of heat in this reaction. And of course it's going to be a negative term because it is still exothermic. And of course this is kilojoules. If I wanted the answer in joules, you could do that conversion. But pay attention to if you're given your delta H reaction in kilojoules versus if it's in joules, just watch what those units are. That can be given to you in different units. So looking at the iClicker question, it's very much the same. But the difference here, we're looking at starting with our H2 liquid. So we have, that means that for every 2 moles of H2 liquid that is reacted with O2 liquid, that we form 571.6 kilojoules. So you can't forget that 2. That 2 is really important. So doing this calculation, we're starting with 1.32 times 10 to the 5th kilograms of H2. And again, we got to calculate that to grams because our molar mass is in grams per mole. So 2. Our molar mass, this is H2, so it's of course 2.016 grams of H2 per every 1 mole of H2. And now we can use our relationship from our change in heat to our 2 moles of H2. We want our moles at the bottom so they cancel out. And then our negative 571.6 kilojoules at the top. And when we calculate that, we get C. I could also figure out if I knew, so I know a lot of things by this reaction. This also tells me a little bit more about the reaction. This tells me how much heat is generated in the forward reaction. But assuming the reversible reaction was possible, I could figure out how much heat would be needed to cause the reverse reaction to happen. Because it's just going to be equal and opposite what this delta H is telling us. So we know a lot more from just this than what we just went through. Now before we really get into that, like I said, pressure can affect our delta H. So what do we do about that? Well, reactions that are done in aqueous solution are at constant pressure if we open them to the atmosphere. Any gas or anything else that's released will be released. The calorimeter is often nestled in foam cups containing solution, and this is more of what you'll be doing in lab when you do this in lab. And we call this coffee cup calorimeter because we could use coffee styrofoam cups, and it's good enough to be insulated enough for us to follow what's happening. Now in this case, our surroundings is still water, but our reaction is occurring in the water because our reactants are dissolved in the water. So this is one of our reactions in solution. So again, our Q of our reaction is going to be equal to our negative Q of our solution. Now in these cases, our calorimeter constant is based on the solution. So you're really going to have to figure that out because it's based on what's dissolved in the water. It's not just based on the water at this point. So typically you'll do a control reaction and actually calculate your your calorimeter constant. Or it might be given to you if you're trying to not take as long in the lab. So every year when I do the Science Olympiad, if I give them one of these, I give them the C constant because I don't expect them to do that and because it's time for an hour. And it is related to our mass of our solution times our calorimeter constant of the solution times, of course, our change in temperature, which is what we're going to measure. Our temperature is going to be in. Now our lid is loose fitting. That allows the pressure not to build up. If the pressure starts building up, the lid just comes off and allows any gas to escape. So therefore, we can do it at constant pressure, and our Q of our solution is going to be equal to negative Q of our reaction. So our delta H, because our pressure is constant, is just going to be equal to our Q of our reaction at constant pressure. And we're keeping a constant pressure by doing this. Now the bomb calorimeter isn't under constant pressure. That's something to note there. because it's tightly sealed. But unless if we're producing a lot of gas, it's not so much of an issue. So to get our delta H of our reaction per mole, then we just divide it by the amount of moles that we used in our compounds. So of course, remember, we can't really measure the Q of our reaction, but we can measure the change in temperature of our water, and our water is the surroundings. Because the water is not participating in the reaction, it's just dissolved our compounds. So let's look at an example of this. Now first we want to know our delta H of the reaction per mole for magnesium. I don't know why magnesium is small there. My thing must have switched it. But magnesium is not supposed to be subscripted. So we want to know for magnesium specifically. And this really will tell us our delta H for the reaction, because 1 mole of magnesium is going to give us our delta H. So if we figure it out per mole, this tells us our delta H for the reaction. Now, we know how much solution we have, 100 milliliters, and we know the temperature change. So assume the density of the solution, because it's water, is 1 gram per milliliters. Now sometimes having stuff dissolved in your water can affect the density, but we're assuming that it's negligible because usually our solute is a small amount compared to our solvent. So really your change in density only comes about when you have a very concentrated amount of solute in your solvent. So we're going to assume that the density is going to be the same as water. Here. So what we're trying to get is our delta H of our reaction per mole. We also are going to assume that the specific heat is that of water, just because if it's dilute enough, that's likely to be true. So what are we given? We are given that we are reacting a certain amount of magnesium. So we have our mass of magnesium, 0.158 grams. We know how much of the water we have, or really of our solution, so total. We know our initial temperature, because our temperature is changing from 25.6 degrees Celsius, and then we know our final 32.8. You should note right away that the solution is increasing in temperature, so it means it's absorbing heat, so that means it's going to be positive, and our reaction is giving off heat, so it's going to be negative. You should right away see that as soon as you see your initial temperature and your final temperature. That gives you information. You're going to have multiple choice. You already know not to choose the one that's positive based on your change in temperature, so you can use this to apply it. We want to know our delta H per mole. So what do we have to do? Well, we know our Q of our solution is mass times specific heat times our change in temperature. Now this is mass of our solution. We know the milliliters of our solution, but hey, we have the density, so we can calculate the mass of our solution. So don't use the mass of magnesium. There's more than just magnesium in here. There's water. Magnesium's dissolved in it. So is HCl, which we're not told anything about. So don't make that mistake. This is our mass. We're measuring Q solution, so this is our mass of our solution times our specific heat of our solution times our change in temperature. So we can figure out our Q of our solution, which tells us our Q of our reaction, because it's just equal and opposite, which we know will be negative because our change in temperature is increasing for our solution. Then we can figure out our delta H. It's just going to be our Q of our reaction divided by moles, because we want it per mole. So starting off, we can figure out our change in temperature. It is going to be our T final minus our T initial. So that's going to be 32.8 minus 25.6. Which I don't have that number written out, of course. So 7.2 degrees C, and of course that's positive. You can put the positive sign if it helps you to make sure that you're remembering your sign. Also, we need to know our mass of our solution. So we know our volume of our solution is 100.0 milliliters. And we know our density, which we're assuming is water. And if that's not true, I would tell you. So we can figure out our total amount of grams of our solution. So we have our mass, our solution. We have our change in temperature. We can figure out our Q. So Q solution, bless you, is going to be equal to our mass of our solution. Don't confuse that with the mass of magnesium. Times our specific heat, our CS, our constant of our solution, which we're assuming in this case we're using 1 of water. So 4.18. Notice this is in joules per grams degrees Celsius. Times, of course, our change in degrees Celsius, which is positive. So this will be a positive number. Grams cancel out, Celsius cancels out, so this leaves us our Q in joules. And this is going to be equal to our Q of our solution. So our Q of our reaction is just going to be equal to our negative Q of our solution. So it's going to be negative 3009.0 joules. Oh, sorry, that's a 6. 0.6 joules. So now this is our delta E for 100 grams of solution. But we want to know our delta E per mole of magnesium. So how do we do that? Well, we can calculate our moles of magnesium because we know how much magnesium we started with. So, and also magnesium, don't confuse it with milligrams when you're looking at it. So we know the molar mass of magnesium is 24.31 grams for 1 mole. So we can calculate the amount of moles magnesium that we started with. So we didn't start with a whole mole, we started with less than a mole. So we expect it to generate, so that's what we're thinking about there. So now our delta E of our reaction per mole of magnesium is going to be our amount of heat generated, which of course is going to be negative. And this is in joules, just a side note, divided by 0.0065 mole. So that's going to be equal to negative 4,000. It's going to be equal to a big number, which is why it asks for kilojoules. So of course we can then convert that to kilojoules per mole. It makes sense that we're not generating as much heat as 1 mole. Our reaction, we didn't use a mole, so we're not going to generate as much heat as 1 mole. So it makes sense that this number is bigger than the amount that we generated because we're not using a mole. So now that we know this, we just calculated our delta H of this reaction. And now that we know that delta H of our reaction, we can calculate how much heat we form for any amount of magnesium we use, or for any amount of HCl, because 2 moles of HCl is going to be equal to, or is going to form still negative 463 kilojoules per mole of heat. So we have information from finding this. So we're going to finish up this chapter likely on Monday. Talking about these relationships that I've alluded to. Y'all have a good weekend. We do have a speaker today at 3:30. She is a chemistry alum doing research in cancer therapy. And I have a little flyer on the Moodle website if you're interested in coming, it should be a really good talk. It's going to talk about her research and answer any questions if you have questions about careers in chemistry.
They told me that they emailed you the paper for me to get extra time on the test.
Oh, yes, they
Okay.